Hello friends, I am NK Jain from Skill on Tech. Today we will learn and discuss about cryogenics and material behavior at cryogenic temperatures. We will also discuss selection of material at cryogenic temperatures in second video of this series. If you like these videos, kindly share it with your friends and colleagues and submit your comments in comment section. What is cryogenics? The word cryogenics stems from Greek "cryos", meaning cold, and "genis", meaning generating. A generally accepted threshold for cryogenics is temperature below 120 Kelvin or minus 153 degrees centigrade. The US National Institute of Standards and Technology considers the field of cryogenics as that involving temperatures below minus 180 degrees centigrade, 93 Kelvin, or minus 292 degree Fahrenheit. At temperatures near absolute zero or 0 Kelvin is minus 273.15 degree centigrade or minus 459.67 degree Fahrenheit. Nearly all molecular motion ceases. Where all molecular motion stops, that temperature is called absolute zero temperature, and that is 0 Kelvin. Here a list of cryogenic fluids is given and with respect to their boiling points in Kelvin. So you can see the air boiled at 78.8 Kelvin or nitrogen boiled at 77.09 Kelvin or minus 196 degree centigrade. It is brittle and ductile materials. It is very important to know that how material behave under cryogenic temperatures or services. Generally, materials used in industries are of two types, ferrous and non-ferrous metals. For example of ferrous metals are cast iron, mild steel, stainless steel, and non-ferrous metals are gold, silver, copper, aluminum, zinc, and many more. We can also classify these materials as a brittle and ductile materials. Here you can see a graph of brittle material and ductile material with respect to their stress and strain. So what we see in a brittle materials, when we apply stress here on a specimen of a brittle material, we'll see up to a certain limit, that is called elastic limit, the stress and strain are proportional. But after this, when we increase stress, there is no yielding, and just after increasing a little stress over here, the material fails and fracture without giving any warning of ductility. In second case, in a ductile material case, if we will see stress strain curve, what we see up to this limit, this is a elastic limit, and if we will remove the stress, the material will come its original shape. But hereafter there is a deformation, plastic deformation, that is called yield point. And after this, without increasing stress, this will be a continuous deformation. Means if we will remove the stress from here at yield point, this will not come to its original shape. And after the yield strength, if we will increase the stress, there will be a strain hardening up to this point, and thereafter there will be a necking in the specimen, and cross section area of the specimen will reduce, and thereafter fracture will occur here at this point. This point is called ultimate strength of the material. So what we see, ductile materials give a plastic deformation, and the fracture occurs in a very last, and it gives a confirmation that the material is behaving in ductile manner. In case of brittle materials, will not give any warning sign of a plastic deformation for a longer time. There is a small deformation and then fracture occurs. So while selecting a material for cryogenic services, it is very important that material must have a ductile properties. It should have a very good strength with respect to temperatures and pressures. Brittle and ductile materials. Ductile materials absorb significant amount of impact energy before fracturing, resulting in telltale deformations. Brittle materials, on other hand, tend to shatter on impact. Tensile toughness is a measure of material brittleness or ductility. It is often estimated by calculating the area beneath the stress-strain curve, as we discussed earlier. When designing equipment for low temperature application, that low temperatures can adversely affect the tensile toughness of many engineering materials. Therefore, while going for a cryogenic service, we must use ductile materials. DBTT, ductile brittle transition temperatures. What is DBTT? I have shown a graph with respect to temperature and fracture energy. The ductile brittle transition temperature is the minimum temperature in which a given material has the ability to absorb a specific amount of energy without fracturing. As temperature decreases, you can see in the graph, if temperature is decreases, a material ability to deform in a ductile material change. This is usually measured using on a case-by-case basis using a Charpy impact test. You can see in this graph when temperature is getting reduced. So behavior of material, here you can see at this temperature there is a ductile fracture, but and this zone, this is a ductile brittle transformation, but here after temperature less than this, towards this zone, there will be a brittle fracture. Extra safety precautions should be taken when working in a crane or oil field applications, low temperature pipeline services in industries, and other cryogenic applications, because when temperature becomes very low, then material behavior will change and metal can fail under a brittle fracture. So temperature conditions are very important while using a material in industries under cryogenic services. Impact testing code for materials. So materials which are suitable for such cryogenic services, impact testing is very important feature. Without impact test, these materials cannot be used. So ASTM E2248-18 V-notch impact Charpy test is carried out to obtain impact strength of materials at desired temperatures in the metallurgical labs. The Charpy impact test, also known as the Charpy V-notch test, is a high strain rate test that involves striking a standard notched specimen with a controlled weight pendulum swung from a set height. The impact test helps measure the amount of energy absorbed by the specimen during fracture. So a picture of a standard Charpy V-notch specimen is given, where you can make a specimen for a Charpy V-notch test, and these specimen can be used, and data of energy absorbed by the during impact test can be recorded, and average energy of 3 specimens is taken as a measure for evaluation of impact strength. Their average energy is counted for this purpose. Behavior of material at low temperatures. So let us understand how material behave at a low temperature. we require DBTT lowest for low temperature designs. The yield and tensile strength of metals that crystallize in the BCC, body centered cubic, depends greatly on temperatures. So where BCCC structures are in the material, they are not ductile materials because they behave in a brittle fracture manner. Iron, molybdenum, vanadium, chromium, tungsten, ferritic and martensitic stainless steel SE 400 series have a BCC or body centered cubic crystal structure. These metals display a loss of ductility in a narrow temperature region below room temperature. When temperature comes below the room temperature, the BCC crystal structure will behave in a brittle fracture. The tensile strength of metals with FCC face-centered cubic structures is more temperature dependent than their yield strength, and the metals often increases in ductility as temperature decreases. So wherever FCC structure is there in the metals, the ductility of the metal will be more and it will remain even though temperature is decreased. For example, metals such as aluminum, copper, nickel, austenitic, stainless steel, gold and silver have an FCC crystal lattice structure and do not experience a shift from ductile to brittle behavior. So a picture of a FCC structure is given in the presentation. You kindly refer this picture. Note that austenitic stainless steel such as SA 200 and 300 series, SS 316, SS 304 have an FCC structures and do not experience a ductile brittle transition. So therefore these materials are very much suitable for low temperature services. That is all for this video. Thank you for watching this video. If you like it, please hit the like button below and share with your friends and colleagues. Please leave your questions, comments and feedback in section below. Thank you.